Okay, so we were talking about this idea of Minimax estimation and its connection to the Bayesian approach. And let me remind you that so in the Bayesian setting, we took an average of the risk relative to some prior on theta, which is like a weighting scheme for your theta. And here we are taking the maximum over theta. So there is no prior, and this is what frequentists usually do when trying to deal with that issue of the risk being a function of theta and not comparable. So I should point this out that the sort of Minimax approach, so Minimax estimation corresponds to finding a decision rule that minimizes this soup is really the maximum. For simplicity, it's like the maximum. So it matches an idea of an adversarial problem or adversarial nature. So remember that there was this game that game theoretic view that we are playing a game with, let's say, nature, that whoever generates the observations, and what we have is a decision rule that so this gets applied to the observation, and then we take the expectation under the distribution of the true parameter. So this view that we have to find a decision rule that minimizes the maximum risk takes the idea that the game is adversarial. So nature goes first, it tries to maximize our loss. So you can think of it as a zero-sum game where whatever I lose, the opponent gains. So the nature gains. So it makes like my sort of nature's loss would be negative this. Okay, I expected loss. So what nature, like you think of it like just opponent. Your opponent is trying to maximize their gain. And so they try to maximize this. So they go first. So whatever decision rule, so you came up with a decision rule, they try to like maximize the risk to maximize the profit. So it's going to maximize your loss. So what rule you should choose then comes next, tries to like, so you have to minimize this quantity, the worst case, because the opponent is aiming for the worst case. So from this perspective, from a game theoretic perspective, it makes sense if the two sides are playing a zero-sum game, but like estimation is probably not a zero-sum game. So nature is not trying to like beat you. So for this reason, people criticize like Minimax estimation as being too conservative. So you're guarding against the worst case. So they're coming for me. So I have to like make sure that like rational nature is trying to maximize my loss. So I'm gonna like find the rule that minimizes that maximum. So that's just the comment. But this like fits very naturally with like zero-sum games in game theory. Okay. So but that's the problem we're going to solve. But from a statistical perspective, the advantage is that we don't need a prior. So there's no ambiguity in defining this. There's just always going to be sort of a supremum risk and maximum risk. And in order to do that, I thought this time do this via this like geometric perspective first. So this geometric idea gives you a lot of intuition, or like geometric / optimization idea. So if you think of the parameter space as being finite, then our risk function is really a vector. We can populate the coordinates of this vector by the values of the risk at the different parameters. So given the decision rule, I get this risk vector, let's say, which I'm denoting as rho delta. And the maximum risk is just the maximum of these absolute value of the entries, which are for now, we're going to assume that the risk is positive. So it's going to belong to the, or not non-negative. So this belongs to the non-negative reals, to the K. So I can put absolute values or not, doesn't matter. And then this is the L infinity norm of this vector. So the minimax problem can be compactly or nicely written in this form, that you're minimizing over the decision rule, the infinity norm of this risk vector. And then we use this idea of duality. There is a dual to the L infinity norm, which is the L1 norm. And the meaning of duality is that if I maximize this inner product of y lambda, where lambda varies in the L1 ball, the maximum is going to keep me the L infinity norm of y, or I can write that inequality in this fashion, which is probably more familiar. They're equivalent in a sense, assuming that the equality holds for some lambda, which is true. So there is just a lambda that makes the two sides equal. It's not hard to argue, and the inequality always holds. That's the Holder's inequality. And so the Holder's inequality is a source of these dual pairs of norms, okay, P and Q, infinity one, and like duality like is sort of you can't say symmetric, but it's like really dual. So dual one, L1 is L infinity, dual L infinity is L1. So it goes back to itself. And L2 is self-dual. So these are interesting facts from sort of theory of norms or convex norms or convex analysis. So what this suggests is that we can replace, because this is now a linear function, like it's bilinear in y and lambda. That's why we like it. So we can replace the L infinity norm here with this lambda transpose rho delta. This is just the inner product. So this notation is the same. So this is really y transpose lambda or lambda transpose y. That's the inner product. So that's what we do. And we end up with this formulation of the minimax problem. So minimizing over decision rules of the maximum over lambda of this. And this has to be over the L1 norm, but sorry, the lambdas for which the L1 norm is bounded by 1. But because this rho is assumed to be in R plus K, so the entries are non-negative, it's not hard to convince yourself that I can restrict myself to all lambdas whose coordinates are non-negative and they sum to 1, like the coordinates sum to 1. Anyone wants to give like some quick justification or like a one-line argument why? So the L1 ball is like in R2. This is the boundary. So it's like a diamond. So the inside of it is the L1 ball. So like 1, -1, 1, -1. So what you're saying is we can restrict ourselves to just this portion, this part, right? And the reason is like sort of obvious because the vectors that you're working with are in this part of the space. So it's really easy to argue, right? So if one of the elements is negative, I can flip the sign and I can increase the objective. And so I can always make all of the entries positive because the corresponding entries here are positive. And also I can always push it to saturate the inequality so that it's 1. If it's not, then I can rescale to push the objective further. So doing a bit of argument like that, some arguments like that would give you that this problem really reduces to min. I'm going to call this set of lambdas PK, which is mnemonic for probability vectors of size k. So these are really probabilities. Any vector that has non-negative entries that sum to 1 is really a probability vector. And so it's actually a probability. It's like a prior, basically, right? A prior on the parameter space. So you can think of these lambdas that have this property as describing a prior on the parameters. And so we're minimizing over delta d, and then maximizing over lambda in the sort of probability vectors, this quantity. Well, let me just write it as lambda rho delta. Okay, so that's our Minimax problem. Minimax. Let's call this, I don't know what we call it, like rho star or whatever you want. So the optimum is the Minimax risk, rho bar star, whatever you want to call this. It's the risk of the Minimax estimate. So far, so good. So this quantity, as I sort of mentioned towards the end last time, what is this quantity? What is the statistical interpretation of this quantity? Expectation of. So this is really
The Bayes risk.
Great, yeah. So this is really rho, if you imagine what this is. So this rho, the elements are r theta I. Delta, this is really the expectation, as pointed out. It's like expectation of r theta delta, right? Assuming that I put a prior lambda on theta. So if I put prior lambda on theta, this is really the average of the risk over the distribution theta. So that's like a weighted average. This is really the Bayes risk. Bayes risk of delta with respect to prior lambda, right? We can use our previous notation. It's like little r of lambda delta if you want. But I'm not going to use that for now. Okay, so this is really a Bayes risk. And how do we connect it to actually the Bayes rule? Is that this problem, so this is a great sort of connection with like convex analysis or like analysis in general. It's a min-max problem. I can pretend to switch max and min. If I do this, and if the equality holds, so assuming that this holds, I have a new problem. So now what is this inner problem?
We're just finding the Bayes estimator.
Right, so this is the Bayes problem because we're minimizing, like finding the decision rule that minimizes the Bayes risk, which corresponding to that prior. So this is really the Bayes problem or Bayesian problem. So the minimum is going to be what we called, so argmin is, so this is going to be really lambda rho delta lambda. So the minimizer is really the Bayes rule, right? So if I call this, I'm using this low lambda, but argmin, if I call this delta. So the minimizer is really the Bayes rule. So that's the Bayes rule that we were studying. So this is really the risk, or the Bayes risk of the Bayes rule. So we ended up sort of solving that, and then now you have to choose the prior. So we are choosing the prior. That maximizes this. So maximizes the Bayes risk. And let's say the prior that solves this is like lambda star. There exists one such that holds. This is a compact space in this case. The objective is sort of, let's say, continuous, hopefully. So in this case, there should be some lambda star. So that would be like the solution of this problem. So if there exists, so lambda star is argmax lambda in PK lambda rho. Okay, and if I can do that, so if that step is justified, and if I can solve this, then this value is going to be the same as the value here. So it's not hard for you to argue for yourself that then this delta lambda star has to be the minimax rule because it achieves the value of the original problem. Right, so lambda star would be the minimax rule, and this prior that we have is going to be it's called the least favorable prior because it just maximizes among all the priors the Bayes risk, the optimal Bayes risk. So it's the worst prior for us. So if someone picks this prior, even if you do the Bayes rule, you're going to incur the Bayes risk. And this is going to be the worst Bayes risk that we can possibly have across all possible priors. So this is called the least favorable prior. So if the above holds, so if let's say this is true, and lambda star that solves the last problem exists, then delta lambda star is the minimax rule. And you can formally show that it's not hard to show it. And then lambda star is called the least favorable prior. It's called the least favorable prior. Okay, so this pairs the problem of solving the minimax, finding the least favorable prior, and then find the Bayes rule with respect to the least favorable prior. So the minimax rule would be among the Bayes rule, but for a specific prior. Sort of, okay. So you see the connection between the Bayes. And so the real key is like whether I can switch that max in, min, and if you're not comfortable with it at this point, this is the value of the problem. This is like in game theory, this is called the value. And so this switching is like whether I go first or nature goes first. So and the problem has a value if this doesn't matter. Whether I go first or like the opponent goes first in a zero-sum game, the answer doesn't change. So there's an optimal like strategy for me and an optimal strategy for the nature. So the optimal strategy for the nature would be to pick this least favorable prior. The optimal strategy for me would be to choose the Bayes rule with respect to that prior. And then we can't beat each other. Like that's the best that we can do in each case, like from both sides. There's a lot of interesting sort of connections to some other areas of like, let's say mathematical thought or like economics and stuff like that, game theory. But let's see why. So this is called, if this equality holds min max equal to max min, this is called, it's like in convex analysis, this is called strong duality. So let me stop, like, see if people have questions. Yes.
In general, greater equal.
Yes, so in general, this is always true. So min max is always bigger than or equal to max min. So this is called weak inequality. If this always holds without any questions, like there's no question marks. So this is called always holds. It's called weak duality in convex analysis. The question is like things would become interesting. So if this is strong duality hold, then this business would work. And so there are general conditions like for optimization problems that people have studied for this to hold. I'm gonna give you like the criteria, which also it's like simple. It's like sort of tautology, but just like it's a sufficient condition to guarantee this. So any other questions before we see that? Yeah.
Just real quick, the argument about you can take the L1 ball and just shrink it to the top quadrant.
Yes.
How did that work exactly?
That comes up because I'm assuming that this is the coordinates of this are non-negative.
Yeah.
So if assume that like the maximum is achieved for a lambda that has a negative coordinate.
Yeah.
Then I can just flip that coordinate, the sign, to be positive, and I would increase this because that sort of term in the sum would like change sign to positive. So there is no reason for like having a negative sign in coordinates. And then saturation always sort of happens in these cases. So I can always like replace without this being non-negative, I can always this with the
String, whatever it gets to that.
yeah, you have because this is like homogeneous, so I can rescale. So if this is not matching one, I can rescale it so that this is matching one, and then would increase this by that fact. So this always is true. So I can replace this here with equality. Okay, good question. Any other questions? So to give you that like the criteria, like let me do the more general thing. And then maybe assign as a whole problem for you to verify that this indeed like does this strong duality. Suppose you have like a problem that you're given this optimization problem that you're trying to solve min, max of f, lambda, and delta. So delta in d, lambda in, let's say some space, in this case pk, but any space. So you want to see whether this is equal to max min. This is like a bivariate. It's not bivariate, but like block bivariate kind of problem. So I want to see whether I can switch the min and max. So the simple criteria is the existence of a saddle point. So if there exists a saddle point, there. So if there exists a saddle point for f, saddle point, let's call this lambda star, delta star, then strong duality holds. So what is a saddle point? Saddle point here is so what is a saddle point? Anyone knows what a saddle point is?
One direction with a max, one direction with a min.
Great. Okay. Yeah. So that's like geometrically, it's like it's a function that if I, for example, look in this direction, it looks like that. If I look in the other direction, it looks like this. You can imagine like it's like a saddle. It's like horse saddle. It's like in one direction looks like this. So in this direction, if I try to look at it, I have a minimum. In this direction, when I look at it, it's a maximum. So imagining it is a little bit. So this is in this direction. It's hard to plot. In the other direction. So this is one of them is like the lambda. This is like, for example, yeah, we'll see which one is lambda, which one is, but that's the idea of saddle point. So this is going to be a saddle point if, so if I like fix, for example, okay. Yeah, so let's say lambda is first. So lambda star delta. So if I minimize over delta, right, fixing lambda star, this is going to be f lambda star delta star. So delta star minimizes if at that second coordinate if I fix lambda star, and also if I fix the second coordinate at lambda star, if I maximize over lambda, then lambda star maximizes the function. So fix one coordinate, maximize over the other coordinate gives me this value, if I basically gives me some, okay, so if I fix delta star, then the maximizer over lambda would be lambda star. That's what this is saying. And if I fix lambda star, the minimizer over delta is going to be delta star. Okay, so this pair has this property at this point. So this is like if this is lambda, yeah, this is delta. So this would be delta star, and this would be lambda. Yeah, visualizing it's a little bit tricky. Delta star. And delta, and then yeah, so this is lambda, and this is lambda star. Yeah, it's very hard to. So I think this direction. So there's this point. If I move in the direction of lambda, I'm going to go up. So lambda delta star minimizes it. If I go in the direction of lambda, it goes down. So lambda star minimizes it over. Sorry, maximizes over lambda. So it's just simple. So in one coordinate, you have a maximum. In one other coordinate, you have a minimum. Right. That's the idea of the saddle point. So I'm not going to prove that this implies strong duality because it's very simple. I'll probably maybe assign as a homework problem, you can verify for yourself. So if there exists a point like that, then these two problems would be equal. So it's a very nice geometric argument. It's not hard to show. So what does this mean, like from a statistical perspective? In our case, sort of F. So proof. So this statement that if there exists a saddle point, then a strong duality holds. Prove as an exercise. So what does this mean for us? So statistically, what does this mean? So F is, in our case, lambda rho delta, right? So so this means there exists a prior lambda star, like a prior lambda star, and a rule delta star such that these two criteria hold. So what does, all right, what do these criteria mean? I mean, these two inequalities. So what do they like mean statistically? Say the first one,
The first one means that you just have a Bayes estimator, right?
right, so the first one means delta star is the Bayes rule with respect to lambda star. So such that delta star is the Bayes rule with respect to lambda, i.e. in our notation, delta star is just really delta of lambda star. That's our notation for the Bayes rule. So what about the second one? So what does this say?
The Minimax estimator or lambda star is the, it's the Minimax.
So the maximum over lambda, this is just, in our case, this would be just the not the minimax, but the maximum risk, right? That's like the Holder's inequality. So this is saying that the maximum risk is equal to, this is just the Bayes risk, right? So this is the Bayes risk. This is the maximum risk. So saying that this holds, first this holds, and second, that for delta star, the Bayes and minimax risk are the same. Or like not the minimax, the maximum risk. Maximum risk. are the same. So it's a particular estimator for which its base risk is the same as its maximum risk. Okay. It's not saying it's minimax, but it's just that it's a particular estimator whose base risk with respect to its prior is the same as the maximum risk of itself. So these two criteria, if they hold, then that saddle point criteria holds, then the strong duality holds, then you have solved the minimax problem. So this delta star has to be minimax, and lambda star has to be the least favorite prior. Yes.
So from the game theory perspective, regardless of who goes first, you're going to choose the same decision.
Each side would choose the same decision. Like decision for the nature is choosing the prior, for us is the like delta. So no matter which goes first, the rational choice is this particular saddle point. That's the idea. Okay. So this is sufficient, but gives you a criteria for finding a minimax rule. So this part we can do. So for every prior, you can usually you have a good idea what the base rule is. We did that calculation. This part is a little bit tricky. So you have to like now massage the prior such that the maximum risk of that base rule turns out to be equal to maximum risk. A very special case of this is where when you choose a prior such that the base risk is like the risk is like flat. Everywhere is the same, so then the average is the same as the maximum. So like a very special case, a very like further sufficient condition. Sufficient condition for 2 is to have a flat risk, flat frequentist risk. So a decision rule that achieves a flat risk is sometimes called an equalizer. So like i.e. delta star be an equalizer.
That's flat in the space of priors.
No, in the like as a like function of theta. So remember this was like the risk, for example, for the so flat like as a function of theta. Right. If the function is flat, the maximum and the average are the same, right? So that's one way of achieving this, but this is not the only way. Another way of achieving this, like you have a function that looks like this. The prior only puts mass on the part that is the maximum. So because you have a prior, right? So that lambda star only puts mass here, and where it puts mass, the risk is sort of flat and equal to the maximum. But this is more like much more fancy. So we're going to work with this simpler case. Yes.
Yeah, I was going to ask that question because from the start it seemed like the way to maximize base risk is just find where the maximum is and put all the mass on that, right? Like that would be the prior that maximizes the risk. Is that not always the case?
So the thing is, once you like where the maximum is, put the prior here. That's the idea. When you put the prior here, that would change the decision. So the base rule with respect to that prior is going to be different. So you start from your decision rule. So it's like a game between like you start from this as the risk, but once I put the prior there, compute the base risk with that base rule with respect to that prior, that's not going to be the original decision rule. That's going to have a different risk. So Minimax sort of like has this optimality. It's like it's with respect to a prior that makes its risk flat. So you have to find that prior that makes the risk sort of flat, or like puts the mass only on the part that's maximum. That's exactly what you have to do. So you can see like it's not easy to find. It's just not so obvious. This idea is sort of clear. So this is sort of the geometric business of. There's more geometry like here, but I usually don't do it this way, but I think this is much more clear. The connection between the minimax and sort of the interesting sort of interplay between optimization, statistics, and these ideas.
That is a special case to achieve the equality, right? So the opening flat prior or like putting a prior on the
Right, not necessarily. Yeah, a special case, so not the flat prior, but the prior that makes. It puts the mass only where the corresponding Bayes rule has maximum risk. So you pick your prior, right? There is going to be a Bayes rule, and it will have a frequentist risk, and that risk might happen to have like its maximum only, like over the prior only gets the maximum. Like it's like maximum is achieved all like over the space of where the prior puts mass. Then you have a Minimax rule. The easiest is like the maximum is everywhere. So everywhere is maximum. Yeah, so sort of. Okay. Any questions? Other questions? Okay, so there's so the slides are doing that. And so this is the business that we mentioned here. This is the two criteria are stated here, and you can prove things like more directly. The proof is not hard. So once you have this, but I did it more generally. So this criteria existence of saddle point might be useful later for you if you do optimization. In this case, it translates into there being a Bayes rule with respect to a prior such that the Bayes risk and the maximum risk of that rule are the same. So this is the Bayes risk of the Bayes rule with respect to lambda, and this is its maximum risk. So if they're the same, then this particular Bayes rule is going to be minimax, that particular lambda is going to be least favorable. And then there's also a business of uniqueness if you want. If the Bayes estimators are unique, that minimax is unique. So this is done in more generality, but the proof is quite simple. You don't have to have like a finite parameter space. I'm going to skip this. And this is the idea that the special case is a Bayes risk, so a Bayes estimator whose risk is constant and equalizer is minimax, or a Bayes estimator is minimax if this is the set of parameters that the risk of delta attains the maximum. So if the prior puts all the mass over that, then it's going to be a minimax. So that's the second thing that we talked about, but we're not going to worry about this. It's much harder to try to engineer lambda in such a way that this happens. So the strategy here would be the weaker one. So strategy would be find an equalizer that's also a Bayes estimator. So something which is a Bayes estimator and equalizer then has to be a minimax rule. Okay, I just want to do a simple example. I think this might be one of the whole problem. I'm just going to go very briefly, like high level, and then the details you're going to figure out. So is this okay? So just very briefly, so I want you to sort of work out the details yourself. So suppose you have like a single Bernoulli variable. It's so difficult finding these that we have to like go from like n to 1. So Bernoulli theta, quadratic loss, theta continuous in 0 to 1. Okay, I'm going to put the general prior on theta. So this prior, like for the beta, could be anything. It will have a first moment and a second moment. So these are the things that matter for like end up being important. So you write down the frequentist risk. The frequentist risk turns out to be for a general estimator, because delta maps sort of 0, 1 to this. So delta is delta of x, right? So it's just equivalent to a vector because they're just two values for x. I can just represent it with delta 0 and delta naught and delta 1. And I don't know the decision rule. So generic decision rule has like these two numbers. So what value I predict for theta if 0 comes out, that would be delta naught. What value I would predict for theta if 1 comes out or comes up, that would be delta 1. And so the risk you would write down. It's not hard to write down. It would be like that. And then you collect as a function of theta. So you collect it as a function of theta. And then when you try to calculate the Bayes risk, you plug a random theta here and take the expectation. If you do that, you'd see that the second moment of theta respect to the prior. So the second moment of the prior comes here and the first moment comes there. Okay. Again, very high level so that you figure out the details yourself. And then I can take, if I want to minimize this over all delta, I can try to differentiate respect to delta 0 and delta 1, so they're equal to 0, and these would come out. Or you can use the criteria that you established, that the Bayes rule is like the expectation of theta given x. Okay, so the conditional expectation of theta given x, because the risk is quadratic risk, that would give you the same answer. But in this case, because it's simple, we can also like differentiate so equal to 0. So it turns out to be that this is going to be the Bayes rule corresponding to that prior. So it depends on the moments of the prior. So how do I now establish an equalizer? So let's say I was looking for an equalizer. An equalizer would make the risk, frequentist risk, flat. So what would, yeah, is there a question?
Yes, sorry, were the first and second moments because expectation of the actual true theta or prior?
So the expectation with respect to a prior that we put on theta, there's no, like, this is the Bayesian problem, right? There's no true theta. So I put a prior on theta. That distribution has the first and second moment, right? When I plug that capital theta here, I get theta squared random, I take the expectation, I get the second with respect to prior, yeah. So that's the Bayes rule, and you can see it depends on the prior. So if I change, it only depends on the first and second moments of the prior, not all aspects of the prior. So how do I find an equalizer rule? So I want a decision rule delta whose frequentist risk is flat. So the risk as a function of theta, I want it to be flat.
So the decision rule is just a constant.
Not decision of the risk. I want this
Risk,
to
yeah,
be
risk.
constant as a function of theta. It's a polynomial in theta. When does a polynomial become constant? I see some possibly. Yes, we have to set all the coefficients of theta to 0, otherwise it's not going to be. So the polynomial is going to vary unless the coefficients of everything except the constant term is 0. So I have to set these to equal to 0. If I set these equal to 0, it gives me two equations in two unknowns. And I can solve those equations. And those equations, if I solve, it gives me this. So that would be an equalizer rule from a frequency perspective. And this is how a general Bayes rule look like. So now if I want to have a Bayes rule, which is an equalizer, what should I do? Yeah, just set these equal, see if I can find the prior whose moments sort of I can engineer so that this comes out. Okay, so I set them equal, so M2 and M1 has to be like 1/4. The other one has to be like, or some like, sorry, this has to be 1/4, the other one has to be 3/4. And then I solve, turns out to be like the optimal moments are this. So these are the moments of the least favorable prior, let's say. And then I have to search for a prior that has these moments, and I'm lucky, let's say there's this beta prior 1/2 that has these moments. So if I put this prior, so everything sort of works out. So I get a decision rule that's an equalizer, and it's also Bayes with respect to this prior. So this has to be the least favorable prior. And the decision rule corresponding to this, which you can evaluate by plugging in these values. The corresponding decision rule, when you plug these values in, would be the minimax rule. Yes.
Doesn't this all depend on choosing a loss function?
It does, yes. That was from the start. Yeah.
Yeah. But so we found the least favorable prior. Is the corresponding Bayes not up to choice of loss function, even though you've picked the least favorable prior?
Yeah, so the least favorable prior is with respect to the loss. So everything is with respect to the loss.
So the loss is fixed.
The loss is fixed, yes.
Yeah.
But it actually depends on more. I'm gonna show you. It's even worse. So it depends also on like what parameter space you pick. But yeah, so that was like from the start. So everything sort of in decision theory relies on sort of up to a certain level, like sufficiency. These ideas are like beyond loss functions, but everything that we talk about the risk, whenever we talk about the risk, like minimax, Bayes, admissibility, they all depend on the particular loss. Okay. Okay, good. And then you can also calculate the minimax risk. It would be 1/16. So everything sort of works out. There is like a Bayes rule here. Questions? You can see it's pretty challenging to find even like.
So for our purposes of like statisticians.
Yeah.
Given just like a random Bernoulli. Our concern is the decision rule, right? So we would choose like 1/4 and 3/4 as the.
What is it? So let's say, okay, what is the rule? So yeah, so M1 star is 1/2. This one is 3/8. So what is delta star 1 here? What was that again? It's like 1/2. I never computed it. So what is it?
3/4.
Yeah, it can't be the other way around, right? Something is missing. Did I make a mistake? Is it correct?
M2 over M8.
M2, right. Okay. 3/8 divided by 1/2, which is 3/4, right? And then delta star 0, what is this? M1 minus, it's like 1/2 minus 3/8. Right? Which is this is like 4/8 minus 3/8, right? Or 1/2. Quarter, right? Yes.
Okay, so that's like the equilibrium. So like nature says, here's a Bernoulli distribution, here's a single data point. And then we choose that decision rule as like that's the equilibrium of the game.
Yes, yeah. So if nature doesn't tell you, like nature chooses this prior. So if it wants to give you like a theta, like choose a theta according to this prior.
Okay.
Right? And then flip, like picks like randomly from this value for theta, and then flips a coin with that like probability and gives you 0, 1, and you decide if it's 0, you say the coin was like the probability was 1/4, otherwise it was 0/4. That's the value, like the optimal play.
It feels weird that the beta distribution is coming up for like a single coin flow.
To be honest, it could be other, I don't know, I haven't tried. This one has these moments. It could be other distributions that have this. I don't know if this is the unique one. I never thought about like. But the fact that this is not uniform is interesting. Right? It's not the uniform rule is not the least favorable prior. You have to like do something else. Like this is gonna have like one of these things around 0. So that's the least favorable prior. Okay, I'll let you contemplate this, the statistical implications of this. This can be generalized actually. So you can generalize it to n samples and then beta n/2, and where 2 would be least favorable. And the associated minimax risk is, so then the decision would be just the Bayes rule split to this prior. And then the minimax risk would be this compared to the sample mean. As you can see, the minimax risk is like flat. Doesn't depend on theta. And it's like asymptotically it's comparable. So it's going to be 1/n. But at, for example, 1/2, this is going to be 1/. So the maximum of this is going to be 1/4n. And this has a smaller maximum. Right. So this is like the maximum here is 1/4, and this is going to be flat, slightly less than this. So the gap is going to go down. Like it's slightly better than 1/4. A lot of work for getting that tiny bit, but it's going to be worse near 0 and 1, but at the maximum would be better. So, yes.
So if the minimax estimator is different than the Bayes estimator, that means the minimax estimator is worse on average, right?
It's hard to say worse than the Bayes. This is not Bayes. So Bayes, there are many Bayes estimators. You have to specify worse than what. I'm going to give you a geometric picture. So what exactly the minimax is might be better to understand. But this is the story for the Bernoulli case. And let's see if I have, yeah, so this, I think probably this is the one that you're going to do in the horror problem. If I change the omega to 1/3 and 2/3, let's say, like it's not all possible values in 0. I just like hypothesis testing. I know that the coin is going to be either, it's like not a fair coin. It's like the probability is going to be either 1/3 or 2/3. I just don't know which one. Then you can go through the analysis and I believe so. In this case, there are many equalizer rules, and then you intersect it with the Bayes, and then you end up that the minimax risk is something like the minimax rule is something else. So that would be your minimax rule rather than previously. So it depends on like your parameter space. So this is like a hypothesis testing problem. The minimax like hypothesis testing rule is different than the minimax rule for the continuous parameter space.
This
Okay.
is a question would follow up to the sort of the difference between the sample mean and the minimax. How often should we expect the minimax to outperform like other estimators, right? Like the sample mean is sort of a canonical choice, right? And so it only outperforms it like only a little bit, right? Basically the maximum. It's not the worst case of the.
Yeah, for small sample sizes, it would be quite considerable. So let's say like 2, 3 or something like that. But for larger, it's so these things are there's like a limit to how well you can do. Like they should go like 1/n. So you can't beat 1/n, let's say, for this family. So asymptotically, so the rate is the same, okay? And in this case, like the pre-factor is also the same, like 1/4. The general story, I don't know. Like usually you don't. You're not lucky enough to calculate the exact minimax rule. So you talk about like the rates, minimax rates. So at what rate the minimax rule goes down, and those you can bound. And so the majority of the work in modern statistics, like frequent statistics, figuring out the minimax rates for different problems, not the minimax rules. So you're saying up to a constant factor, I achieve the same rate as the minimax rule. So this is going to be a minimax rate optimal because the rate is the same as the minimax. So this is good enough for modern statisticians. Like it's too hard to figuring out exactly the minimax rule. Anything that achieves the same for like higher dimensional problems, like problems in like with high dimensional parameters or functions on function spaces, even the rate is not obvious how to achieve the rate that matches the rate of the minimax estimate. But that's where the game is. Right. So any other good, yeah.
Why you choose the equalizer? Why you choose with the one that doesn't depend on the theta? Should it be the
Because that was our like the story that we told ourselves here. So we convinced ourselves that okay, so this is yeah. So if you have a saddle point, and you have a saddle point, if you have a Bayes rule whose Bayes risk and minimax risk are sorry, maximum risk are the same, and is sufficient condition for like a Bayes risk and maximum risk being the same is that the risk being this flat. It's like average, like constant functions have the same average and maximum.
could you do better, like for your nature, like better than a constant?
If you can find something like that, this is going to be a minimax. So then the question is that whether the minimax rule is, so this is, if you manage to find an equalizer rule, which is Bayes, if A holds, then that has to be minimax. So you can't do better than this. There could be other estimators that are also minimax. So that would be non-uniqueness then. But if it turns out that the Bayes rules are unique, then the Minimax rules are unique. That's like the content of this result. Then you can't even find another estimator. Like there's a unique Minimax rule. So if you're lucky enough that this procedure that you described yields a result, then you're done. So you're not going to improve that. Okay, good. Any other questions? Okay, so let's. So I already covered this sort of. So I'm going to come back to this picture. That's like the summary of the whole business. So that's the thing that we did. I just want to point out that if you, this is like the finite case, if you also allow randomized decision rules, so the set of all the risk vectors under as we vary the decision rules, let's call this the risk set. If you allow randomized decision rules, then that set is going to be a convex set. So randomized decision rules means deterministic rules, you remember. So if I have an observation, I have a deterministic decision. Randomized decision rules have a randomized decision. So you observe, let's say, the coin flip, your decision is not going to be like exact. You may flip another coin to decide. So by randomization, basically you can achieve any risk between. So if you have rho delta 1, that's the risk of one risk vector of one estimator, and the risk of another one, you can interpolate between them by randomization. You flip a coin with like probability alpha, choose delta 1, probability 1 minus alpha, choose delta 2, and the risk would be, it's like alpha rho delta 1 plus 1 minus alpha rho delta 2. This is easy to show. Okay, so if you randomize by like changing the probability of the coin flip, you can traverse this entire line. So that means that the risk set is going to be a convex set. So the problem that we're actually solving, because the space of priors is convex, then in this case under randomization, so if you allow all the randomized rules, the risk set is also be convex. So it's like a very nice convex saddle point problem. So the other thing that I all covered this. The other thing that I want to mention is this interesting idea that says in this case, so in general, a unique Bayes rule is admissible. In this finite case, there is a complete answer. So if you have a like finite parameter space, then if the prior is if the prior is, so you have a prior, all the entries of the prior are strictly positive, then the corresponding decision rule is admissible. The corresponding Bayes rule is admissible. So the Bayes rule with respect to a prior that puts mass everywhere is admissible. This is easy to show. This two-line proof, you can show it for yourself. The opposite is very interesting in this case, that if you have omega and there is an admissible rule, then that has to be Bayes with respect to some prior. Okay, so the answer is the admissibility. So admissible rule is among the Bayes rule, nowhere else. So the proof of this is a little bit tricky. Let's see if I want to maybe mention a few words about this. So the way to show that, maybe like a very short idea of the proof, why an admissible rule has to be Bayes. If you have, so let's say delta is admissible, fixed delta, and then let X be the risk vector. Okay, so let's say you have two parameters. So just theta 1, theta 2. So there, this guy is going to be in R2, right? So this is just X is risk of theta, like risk of delta for theta 1 and theta 2. So that would be some X in the X1, like in the plane, it would be like X1 and X. So this would be X1. So the X2, that would be the risk of this guy. And then I'm going to look at this set, R2, this set of all y that the coordinate y is less than X. So that would be this set. this set would be everything that's there, and then I'm gonna also subtract this particular point from it. So like, or exclude the point itself. So that's this part. So that's QX. So removing one point from this is going to preserve convexity. This set is still convex, although it's not closed, but still convex. So this boundary is there except that point. So now admissibility means, so there is also a set S, which is this is the set of all, this is the risk body, that all possible risks of all estimate, like randomized decision rules. So that's a convex set. The admissibility means that they're not going to touch. So that would be a convex set. Could be like this, or like could be. So this X has to be in that set, right? Because X is a valid decision rule. So at this X has to touch that set. But there's this convex set, which is S, that's the risk body. This is the set of the risk of all, like the risk vectors of all possible decision rules. It has to include X, so you touch this. But once I remove that point, then they're not gonna like intersect at any other point. So why is that? So admissibility implies that these two sets are not gonna intersect. What happens if they intersect at a different point? So if there was an intersection, then it wouldn't be admissible because there is a risk, there is a decision rule here whose risk is strictly better than this in both directions, right? So these are basically the red part, or the QX is the set of all possible risks that would make this guy admissible, right? If there is a decision rule here, then if the decision rule with the risk here is going to make the one that we have under consideration inadmissible, because both components of the risk are lower. By definition, for every parameter, we're lower, right? So that makes it in. So admissibility means that there are these two convex sets that are disjoint. So then there's this general result that I can separate them by hyperplane. So there exists a hyperplane that separates them. Geometrically, it's clear, but these are high-powered sort of convex analysis results that if you have two convex sets, let's say one of them, so two non-empty disjoint convex set can be separated by a hyperplane. So there exists a hyperplane. So there is this normal to the hyperplane, let's say U. So U transpose Z is less than U transpose Y, where Z is Q in QX and Y in S. So that's the meaning of separation. So there is this vector that I can make non-zero, such that for every Z is like here less than for every Y and that. And then you can argue similarly as what we did before, that these U has to have non-negative coordinates. It's not hard to argue that. And if it has non-negative coordinates, and because it's non-zero, I can divide by the sum of the coordinates, and that would give me a probability. So I divide this by the sum of Ui less than or equal to. So you can call this lambda. This is now going to be a prior. And because this holds for any Y in S, so lambda transpose Li is less than minimum over Y in S of lambda transpose Y. And this is basically saying that this guy is the Bayes rule with respect to lambda, because this is minimizing. This is so these are the risks, right? All the possible. So this is the risk of the estimator that has this risk rate. So sorry, the Bayes risk of the estimator that has this frequentist risk. So this problem of minimizing this is the Bayes problem, and this is less than or equal to. So it shows that I'm sorry, what did I say? Oh yeah, so okay, so this is less than this, and then I have to yeah. So this holds for all z, not in qx. So these z's might not be like valid risks of estimators, but I can find a sequence in qx that converges to z to x. Sorry, so pick a sequence in qx that converges. So this holds for all z in qx. Pick a sequence that converges to x, and then take the limit. That would be lambda transpose x is less than or equal to that min. So this is the Bayes risk of our estimator, and this is the best possible Bayes risk. So this shows that this estimator has to be Bayes with respect to this lambda. So the choice of the prior basically came from the separation idea. Okay, it was fast, but you can figure out the rest. Right? The main idea is that admissibility makes me do this separation, and the direction of the separation gives you the prior that you have to choose. And then it's easy to show that with respect to that prior, the rule is going to be Bayes. Okay, so so this sort of completes the picture. So that's the picture that we get. So these are, let's say, I think this is for the Bernoulli case. So these are the risks of all deterministic rules, and then you take the convex hull, that would be the risk body. What we showed is that so the red points are the Bayes rules. Why they are the Bayes rules? Because these are all the admissible rules. So anything inside this is not going to be admissible because I can sort of go down. Okay, so if you imagine any point here, if there are any other point here, it's not going to be admissible. So I have to move all the way to the boundary. So the boundary of this risk body is basically all the admissible rules. And it turns out that they're also the Bayes rules, because the Bayes rule, what it does is you're basically minimizing these hyperplanes, lambda transpose times x. So the set of all decision rules such that this is constant is a hyperplane. So if I like move this, if I want to minimize for a fixed lambda, if I want to minimize Bayes error, I have to move this all the way so that they touch the boundary. So geometrically, the Bayes rules are at the boundary, and also the admissible rules have to be at the boundary. So this also geometrically tells you that you end up at the boundary. So whether you're admissible or you're Bayes, you're going to end up here. So where is the minimax rule? The minimax rule is like gonna be, how do I find the minimax? So okay, so minimizing the Bayes risk is like moving these hyperplanes. So these are the level sets of lambda transpose x. What are the level sets of the L infinity ball? So I have to like minimize, let's say, x infinity over x in S. So this is the Bayes problem is for prior is this. So this is the Bayes problem. This is the minimax problem. So the Bayes problem is basically minimizing a linear function over this set. The minimax problem is minimizing the L infinity ball. So I have to look at the level sets of the L infinity ball. So level sets of L infinity ball, what do they look like? Like they're like, these are level sets. So they have to pass through the 45 degree. All right, this is one level set, this is another level set. So I'm going to minimize by moving these until I hit the boundary. So that would be the minimax one. So you can see the minimax is also at the boundary, and it's also on the 45 degree line. The 45 degree line, those are the equalizers. So everything is like here is an equalizer. Everything here is Bayes and also admissible. This very sweet spot is the minimax. Okay, and geometrically you can see what happens. So for the Bayes, we're minimizing the, like if you like minimize with like different priors, you're gonna hit the boundary at different points. There is this specific prior, like orthogonal to this 45 degree. That's the like least favorable prior. If you minimize with respect to that, you're gonna hit the boundary. You also like minimize with respect to like the infinity, you're gonna like hit that point. So geometrically, so everything should be sort of clear once you like think of the picture like that. Right, so these are this like simple Bayes problem, Minimax problem. You can do level sets, you'll do all sort of cool stuff. But this tells you that this Minimax sort of occupies a very sweet spot. Okay. And the Bayes rules are also like occupying a very nice spot. So it's like the face of this that points towards the origin. And that sort of, I think, sums up the relation between the Bayes and Minimax. Okay. At least geometrically gives you like a picture. This very simple. Questions? Comments? Okay, I guess we're,
Actually, a question.
yeah.
Is the interior of the risk body done empty, or are we looking at the boundary of the risk body, like with the dots?
The interior, so the way to look at it is to look at the convex hull. So that would be the what? The risk body corresponding to all the randomized decision rules. So I'm not sure. For example, I'm not sure if this is bounded or unbounded. But if these are like, if this is the case, if these are the only things that are possible, then it would look like this. But I'm not really sure. So really, this side is not that important. This side is what matters. So what about the emptiness? So did you?
Is it like, are we looking at the boundary only, or is it like filled in?
No. So all of these like little dots here are decision rules. So you can, this was plotted, I guess, by just plotting this, or maybe this one, I think probably for this. So in this case, you have two parameters, and this is the risk. So you can plug in different delta zeros and delta ones, and then you get these two like coordinates, and then you plot that up. Each one of them is a decision rule here, right? It's not empty. And anything in between can be realized by randomization. Okay.
Because that plot is in 2D, just kind of looks like a 3D surface if you squint your eyes, right? So this is just a 2D plot of D0 versus D.
Yeah, it's suggested that it's like projected from some other.
Oh,
Yeah, but it's 2D. It's 2D.
Yes.
Yes. Like it's coming from a polynomial, so it's like that. But yeah, I can't say much about why it looks like this, but that's what it looks like. Okay, I guess we're out of time. See you next time. Hopefully start something new.